So, in this session we will be discussing about the Rtd profiles of ideal reactors, right, and with lot of variations like if I attach a bypass line to that Cstr or PFR, what will be the change in the Rtd profile if it has got a dead volume or both, right. So, these we will initially discuss, and next we will go for the use of Rtd, understanding the use of Rtd in analysis of real reactors. So, the point is, see, first let us start our discussion with PFR. So, Rtd, our topic is Rtd in ideal reactors. So, first it is PFR, the Rtd of a PFR. Now, you see PFR is a reactor with no axial mixing. Ideal reactor with no axial mixing. Now, whenever we are not having any axial mixing, what will happen? Whatever spike we are giving at the inlet, right, the same spike will travel through the reactor without any dispersion, and similarly after the residence time the same spike will appear at the outlet of the reactor. Okay. So, we have discussed about the two modes of Rtd profile. One is the pulse mode, which we have idealized as impulse function, and another is a step mode, which we have idealized as the ideal step function, which is alternatively referred as Heaviside function. So, you see mostly we will focus, as I mentioned in the previous class or previous session, that mostly we will focus on pulse function, because the pulse has got some advantages over the step input, or rather it is a disadvantages inherent in the step mode of experiment. What are they? In the step mode of experiment, it is quite difficult to keep the sustained concentration of the tracer at the step height C0 throughout the entire duration of experiment. Secondly, it requires a huge amount of tracer, and third, you know that once we have used this step mode, we will not get the E curve initially, we will get the F curve, right. Upon normalizing this concentration at the outlet by the step height concentration, that is C0. So, we will get the F curve, and from F curve is not directly can be used for this further analysis when we will see it when we go for these models, mixing models, right. We will study this mixing model, then you can see that F curve as it is cannot be used. It must be converted to E curve for the step experiments. So, from conversion of F to E, that needs numerical differentiation. Okay. So, these numerical differentiations are prone to large error. So, that is the one of the fundamental disadvantage of the step mode of Rtd experiment. So, that is why in standard experiments of Rtd, we mostly do it with this pulse input. So, if I am using a pulse, its idealization is Dirac delta function. So, think I have a reactor, and here is the tracer input, and from here we are analyzing the output concentration. So, tracer output, right, and it is a PFR. So, definitely as we do not have any PFR in real life, we have to derive the expressions of the Rtd curves, like mostly the E curve conceptually. So, what we are giving at the inlet? C in versus T, it is a simple spike, right, at T equal to 0. So, that spike will travel, and finally at t equal to tau which is basically V divided by V naught, right. So, it has got the residence time tau, which is V divided by V naught. V naught is the flow rate of the inert or the reactant, whatever. So, at t equal to tau, the spike will appear. So, this is C. Okay. Now, this is not the typical unit impulse, because the area under the curve is not exactly equal to 1. Why? Because the spike what we have given, it is this infinity multiplied by some infinitesimal amount of time, and actually you see it is an idealization of typical pulse input. What we are doing actually, there are two steps of idealization. Actually this C in versus T, it is like this, right. So, there is certain area under the curve, and the area, this A, is 0 to infinity C in T dt, right, C in T dt, and that area, we can obtain this area if I know the amount of the tracer injected. What is the amount of the tracer? Say the amount of the tracer injected is 0 to infinity C in into V naught into dt, where V naught is the volume flow rate, right. So, we can understand this area is equal to m divided by V naught. So, area under the curve we know, right, area under the curve we know. So, this function C in, whenever we are idealizing, what is the intermediate step? We are thinking that okay, we are giving in the form of a pulse which has got the area A, right. This is intermediate idealization. And next, if it has got a span capital T and height h, we set a condition that h tending to infinity and t tending to 0, and we got this spike. So, C in, you see, can be written as A into delta of t, where the area under the curve here will be simply A, right, because the delta's area will be, here A is constant and the area under the delta or the Dirac delta function is simply unity. So, C in here is A 0 to infinity delta t dt, sorry, this is integral I, right, and this I we can write that this I is equal to A as 0 to infinity delta t dt is equal to 1. So, the same spike will appear at the outlet. Now, if I divide it by area, the same spike, the C is equal to basically the same, but there is a difference. Actually, we cannot write it. C we can write as A into delta of t minus tau, right, because it has been delayed by time t equal to tau. So, E, which is Ct divided by 0 to infinity Ct dt, must becomes delta of t minus tau. So, that is our understanding that E will be equal to delta of t minus tau, the Dirac delta function, right, which has been delayed or it is shifted from t equal to 0 to t equal to tau. So, if this is the E curve of a PFR, we have to calculate what will be the F curve. So, E curve, E versus T is this, the spike at t equal to tau, and E as we have noted the delta of t minus tau. Now, F, you know, F is basically 0 to t et dt, right, 0 to t et dt. So, we have 0 to t delta of t minus tau dt, and that must be equal to 1 if t is greater than tau and equal to 0 if t is less than tau. So, F curve of a PFR will be like this, a step function. At t equal to tau. And what will be the mean residence time? We know from our previous discussion that mean residence time Tm is 0 to infinity t into Et into dt, and that is equal to 0 to infinity t into delta of t minus tau into dt. And there is a property of the delta function that minus infinity to plus infinity, actually it is a general limit for this delta function. Here minus infinity to 0 has got no specific significance because t is time, right. So, gx into delta of x minus tau dx is equal to g tau. So, here gt is equal to t and here delta of t minus tau, so it will be equal to tau. So, Tm equal to tau, and sigma square 0 to infinity t minus Tm whole square, this delta of t minus tau dt. So, it is tau minus Tm whole square, which is equal to 0 as Tm equal to tau. So, there is no spread because sigma is a measure of spread of this distribution. As we can understand, the Dirac delta function is a spike, it has got no spread, it has this perfectly compressed, right. So, that is about the single PFR without any dead time or bypass. So, you have got the E curve, we have got the F curve. Okay. So, now we will think of a PFR with channeling, that means it has got a bypass and bypass line has got 0 residence time. So, PFR bypass line is theoretically being considered. These are all basically the theoretical analysis, never happens in reality because we cannot actually construct a PFR. So, what will happen? Here we considered the PFR with a bypass line and this volume flow rate, the total volume flow rate to that setup is distributed. One is going to the reactor and another is passing through the bypass line. So, topic 2, PFR with bypass line. Bypass line has got no residence time. So, what is that? Let me first represent the schematic. Volume is V and this is the bypass. Right. Now, the total volume V naught is distributed as, let me use the same symbol as I have used in the text. So, V of B, bypass, and V SB, right. and this is again V naught. So, you see, when we have two reactors with two parallel branching, here we must understand this. How to find out, this is very important, how to find out the E curve of a system with parallel branches. See, I have two reactors. This is R1, this is R2, right? Delivering the product. Here we have V naught, this is V1, this is V2, right? So, overall E, what we are getting from here, from C curve to E curve, what we are supposed to get for pulse. So, E curve is equal to V1 by V naught, E curve of individual reactor R1 plus V2 by V naught, that of E2. Right. This I am not proving, it is quite understandable and simple. So, here how we can write the E curve. So, E curve will be, say this has got or VB, EB has got a function delta t, because as the residence time is 0, once we give the spike, the same spike will appear instantaneously. So, we can write it is VB divided by V naught into delta t plus, here we know that VSB divided by V naught into delta of t minus tau SB. Tau SB is different from tau. Tau SB is equal to V divided by VSB, whereas tau is defined as V divided by V naught. So, VSB, you see it is lower than V naught. So, tau SB is greater than tau, right. So, what will be the E curve? Say this is t equal to 0 and this is t equal to tau SB, somewhere intermediately we have tau. So, here we will have a spike, here again another spike, right. So, these two spikes will contribute to the overall RTD. Here the area definitely will be VB divided by V naught, and here the area under the curve is VSB divided by V naught. Right. Now, if I look for the F curve, we have to integrate. Now, from here there is no curve, no such y value, e value. So, it is 0. Once it faces this spike, it will move up by VB by V naught, right, because the area will be VB by is equal to VB by V naught. Next, it will move unaltered up to t equal to tau SB, and here it will move up by additional VSB by V naught amount reaching 1, because finally the F value must be equal to 1 at infinity. So, this is 0. So, this is t equal to 0, this is t equal to t is tau SB, and intermediately we have tau. So, it will move up and then again move up to 1, right. So, this is 1, this is VB divided by V naught. So, this much must be VSB by V naught. And we have to note that V is not equal to VSB plus VB. So, obviously, sum of these two must be equal to 1, as 1 is equal to VSB by V naught plus Vb by V naught, right, because of which it is equal to 1. So, that is about the PFR with dead volume, sorry, BFR with bypass. Now, in the handout I have solved separately for PFR with a dead volume. Now, think of PFR with bypass and dead volume, right. I am skipping this PFR with dead volume, it is quite simple. See, if I have a dead volume, right, the effective volume will be this V minus this dead volume. So, as the effective volume decreases, your residence time will basically decrease, residence time will decrease, and we will have, if it is PFR with dead volume, we will have the spike somewhere over here, right, somewhere over here. So, let us see what happens. PFR with bypass line and dead volume. Right, and schematically how it can be represented. Yeah. So, this active volume is VSD, right, this is VB, and we have see, we have a dead volume here, which is VD. So, VD plus VSD is equal to V, right. Tau is defined as V divided by V naught, okay, and V naught is equal to VB plus VSB, okay. Now, tau prime, we are using this, okay, let us use this tau prime. Tau prime is VSD by VSB, right. So, what will be my E curve? Directly we can write E will be equal to VB divided by V naught into delta T plus VSB by V naught into delta of T minus tau prime. Now, VSD you can understand that V minus VD and here V naught minus VB, right. Now, V by V naught equal to tau. So, if I just take tau, so tau minus VD divided by V naught and 1 minus VB by V naught, right, and that is tau prime. Now, whether tau is greater or less than tau prime, that depends on the values of individually the VB, VD, V naught and this VD, okay. So, you cannot say whether it is tau prime is greater than tau or less than tau. If I increase this flow rate in the bypass line, right, what will happen? Your tau prime, this I am increasing this, so tau prime will decrease. See, if VB I am increasing, your tau prime will decrease. If I am increasing VD, sorry, tau prime will increase, and if I am increasing VD, tau prime will decrease, right. So, the E curve will be very similar to that what we have drawn. So, E curve will be this and this. This is t equal to 0, this is t equal to tau prime. Now, whether tau will be placed on the left hand side of t equal to tau prime or right hand side of t equal to tau prime, that depends on the individual values of these VB and VD. And similarly, if I have F curve, it will be like this. So this value is 1, here the value is this, what it is, t equal to 0, and this is t equal to tau prime, and the value here is Vb by V naught. Right. So that's the PFR with bypass line and dead volume. But if it is purely a dead volume, simply we will have a single spike here somewhere at a point. If tau is placed somewhere here, then tau prime we will have a single spike which will be appearing at a time smaller than tau, right? Because dead volume actually reduces the effective volume, and tau, as it is proportional to the effective volume, that will decrease. So tau prime will be in that case lower than tau. So that's about PFR. So let's now move on to Cstr. So third one is Cstr without bypass or dead volume, right? So what we have here, a Cstr, let me draw the schematic. Here we have the flow rate V naught, this volume is V, and it's moving out. Here we have given the tracer C inverse is T as a spike, T equal to 0. And here we will be getting this C curve, and that we have to find out, right? So its volume flow rate is V naught, and we have injected all the tracer at T equal to 0. So we will write a tracer balance equation. Its accumulation equal to inflow minus outflow. The tracer is non-reactive, so there is no reaction term. So under this condition, what will be the accumulation? V into dC dt, C is the tracer concentration, and C here, look, C here and C here, they are same, because Cstr is a well mixed model of reactor. So inflow is 0, because we have injected all this at T equal to 0, and outflow is V naught into C. So here tau into dC dt is equal to C. So obviously we will be getting that Ct equal to C naught into e to the power minus t by tau, where Ct is equal to C naught at t equal to 0. So it's an exponential decay from a concentration C naught. So once we have got the C curve, we have to generate the E curve. So Et is equal to Ct by 0 to infinity Ct dt. So it is C naught into e to the power minus t by tau, 0 to infinity C naught into e to the power minus t by tau dt. So C naught cancels out, and e to the power minus t by tau, and here in the denominator e to the power minus t by tau divided by minus 1 by tau, 0 to infinity. Right. So for infinity it is 0, for 0 it is 1 with a minus sign, so minus minus cancels out, and tau will appear in the denominator of the overall expression, and we will be getting 1 by tau into e to the power minus t by tau. So, E curve is this, right? E curve is simply very similar to C curve, but it will start from 1 by tau, right? And what will be the F curve then? F curve, Ft, is 0 to t et dt, So, that is equal to 0 to t 1 by tau e to the power minus t by tau dt. So, if I integrate, it will be e to the power, see, what will happen? It will be 1 by tau into e to the power minus t by tau divided by minus of 1 by tau 0 to t. So, this tau cancels out and we will be having 1 minus e to the power t by tau, because the minus sign is included in this integration, and from here we get the F curve. F versus t, and this F infinity is equal to 1, which satisfies the property of this F curve. So, it will grow like this and will saturate. So, it is 1, right. So, typical exponential growth we will have. Now, number 4, the same CSTR with a bypass line, CSTR with bypass line. So, here what we will have? And this is the outlet, and we have a bypass. So, total volume flow rate is V naught, this is VB, this is VSB, the volume is V, right. So, tau is V divided by V naught, whereas tau SB is equal to V divided by VSB, and similar to the previous analysis, this will be greater than tau, right. So, what we will have directly as E curve? E curve will be this VB by V naught into delta t, the spike will appear, plus VSB by V naught 1 divided by tau SB into e to the power minus t divided by tau SB, right. So, you see that this can be further simplified as VB by V naught delta t plus VSB by V naught 1 divided by V divided by VSB, right, into e to the power minus t divided by tau SB. That is VB by V naught into delta t plus VSB square divided by V into V naught e to the power Vt by tau SB. Okay. So, we will have this sort of curve. We will have a spike, this is E curve, we will have a spike at t equal to 0, and it will degrade to some value, and after that it will decay. What is that value? This is equal to VSD square divided by V into V naught. Right? So, that is the curve, and similarly you can solve for the F curve. I am not going into the detail, because the F curve, if you integrate here, this will be giving you a spike. Like the form of this F curve, as you can see qualitatively, there will be an increase, and then from here it will start an exponential growth and will saturate. Right. And this value is VB by V naught. So, the rest is 1, and it will grow and saturate to 1. So, that we can easily solve from here. Okay. Yeah. So, that is the CSTR with bypass line. Next, we can think of CSTR with a dead volume. CSTR with a dead volume, what will happen? If we think only of dead volume without considering the bypass line, as we did in case of PFR, here, what will happen? It is pretty simple. 5 CSTR with a dead volume. Sorry, 3, 1 first PFR, second PFR with bypass, third PFR with bypass and dead volume, fourth pure CSTR, fifth is CSTR with bypass, this will be 6. Yeah. So, okay. So, here the notation is CSTR with dead volume tau ST. So, this is VSD. Here we have V naught moving out. So, V is equal to VSD plus VD, tau is equal to V by V naught, and tau SD is equal to V SD by V naught, which is V minus VD by V naught, which is tau minus VD by V naught lower than tau. So, what will happen? This E curve we can directly write as 1 by tau SD into e to the power t divided by tau SD. Right. So, tau SD is higher than tau. So, E curve this is 1 divided by tau SD. Now, tau SD is lower than tau, so 1 by tau SD is higher. So, this is 1 by tau, right, and this tau is higher. So, here the delay will be gradual, right. Tau SD is lower than tau. So, 1 by tau SD, sorry, 1 by tau SD is higher, yeah. So, 1 by tau SD is higher and it is negative exponential decay. So, the delay will be faster in case of Cstr with dead volume, whereas in case of Cstr without dead volume, the curve will be something like this. So, this is Cstr with dead volume and this one is Cstr original without any dead volume basically. So, that is all about the Cstrs with bypass and with this dead volume. Now, for non-ideal reactors, okay, we must understand some of the curves. If it is a tubular reactor, without packing, that means catalyst, right. So, there will be axial dispersion. This is the, it will be very similar to that of PFR, but obviously there will be dispersion, right. This is for ideal PFR. But if it is a tubular reactor, it will not be a spike, it will be spread to some extent and we will have a curve like this, more or less a symmetric curve. Okay. So, this is the real or non-ideal tubular reactor with axial mixing, definitely. Right. Now, if you have a packed bed, that is a catalytic reactor, catalytic tubular reactor. So, here we can have channelings. Single channel path or multiple, right. So, if I have multiple channel pathways E versus T, we can think of this sort of curve. So, these two spikes, two channels. Now, if it has got dead zones, dead zones means once the reactant enters the dead zone, it will be released from the dead zone slowly and over a prolonged interval of time we will be getting concentration, non-zero concentration at the outlet of the reactor. So, if I have a dead zone, it is specifically marked by a long tail of this Rtd curve. So, it will be a kind of thing like this, right. Representative of dead zones. this is a long tail in the RTD curve, which basically indicates that there is a dead zone in this reactor. Okay. Now, on the other hand, tank reactor with bypass, there is short circuit pathway and dead zones. So, what will happen? It will be a spike like this, and then it is like this. So, you see this spike very close to 0 represents this bypassing. This represents bypassing, and the long tail represents dead zones. So, that is some diagnostic approach, non-quantitative, some qualitative diagnostic approach, that if I have this sort of RTD curves, so you can identify actually that what is happening inside the reactor, what non-ideality actually cropped in the reactor, right, during operations. It may happen that over this initial period after commissioning, the reactor is providing its full duty, it's generating output which is exactly equal to the design conversion, but with time this conversion drops. So, definitely we have to note that either there will be a bypassing or there will be formation of dead zones and something like that. Some non-ideality is actually being generated due to operations, right, due to this heterogeneity in this packing, due to some malfunctioning of stirrer in this tank reactor. So, because of that, once we have to go for online RTD analysis, and if I am getting this sort of RTD curve, we know that what are the identifiers, what are the signatures of these non-idealities like bypass or this long tail, what they actually represents, multiple spikes, etc. Okay. So, before we go for a series combinations of ideal reactors, let us have a discussion regarding the Cstr. See, Cstr, it is what? Ct equal to, Et is giving an E curve equal to 1 by tau e to the power minus t by tau. So, if I go for this RTD curve plotting for different size Cstr, we will get different exponential curves. But our understanding about the Cstr indicates that these curves must be identical, independent of the size, right? Because this RTD represents that what is the distribution of residence time. Now, once it is a well mixed, perfectly mixed continuous tank reactor, then we must have the similar or the same or identical RTD curve for different size Cstr, and that can be actually achieved if I go for normalization of this RTD curve. You see, the tau has got a dimension of time, right, and E is a probability distribution function and Et dt is the probability, right. So, E, the dimension of E is simply time inverse, because Et dt is dimensionless as it indicates the probability. So, tau into E is equal to e to the power minus t by tau. Let dimensionless time be defined as t by tau, and tau into Et is dimensionless. We call this entire group as E theta, and this is e to the power minus theta. So, here this E theta versus theta plot for all Cstrs are identical. It will start from 1 and exponentially decays to 0. So, this is the idea of normalized RTD function, though we have derived it from Cstr, but actually it is valid for every reactor. So, concept of normalized Rtd function, right. So, that is the basics of normalized Rtd function. Let us, with this understanding of normalized Rtd function, it is an intermediate topic. Let us now analyze this Rtd curve of a Cstr linked in series with a PFR, right. And we will change the sequence and we will see that what changes we are actually getting in this residence time distribution function. So, PFR Cstr in series, Rtd of PFR and Cstr, right. So, you see that let us first have the Cstr and then a PFR. Here the volume is V1, this is V2, the volume flow rate is V0. So, tau 1 is equal to V1 by V0 and tau 2 is equal to V2 by V0, right. This is Cstr, this is PFR. So, if I give a spike here, C in versus T, a spike at T equal to 0. Intermediately at this outlet, we already know for a single Cstr, we will receive this sort of curve C1 T versus T, and this curve is C0 into e to the power minus T by tau 1. Now, if I am feeding this exponential decay concentration curve to this inlet of the Cstr, the same curve will be regenerated at the outlet, but it will be delayed by time tau 2, which is the space time or the residence time of the PFR. So, we can understand that at this outlet we will have this, let us say T equal to T2, and we will be getting a curve like this, right, and this is C0. So, Ct or Ct is here is equal to C0 into e to the power minus T by minus tau 2 by tau 1. It is just like that. So, E curve is 1 by tau 1 into e to the power T minus tau 2 by tau 1. Okay. That is the E curve, and we have the E curve just like similar to C curve, but there is a change in the numerical value. So, this is T and this value will be 1 by tau 1, and E is 1 by tau 1 into e to the power minus T by minus tau 2 by tau 1. Now, if I think of now a different sequence, first this PFR followed by a Cstr, this is V2, this is V1, and again tau 2 and tau 1. So, now we are again giving a spike at the inlet, C in versus T, the same spike, T equal to 0. So, at the intermediate point, C1T versus T will be the same spike, right, but it will appear at t equal to tau 2. And now this spike at t equal to tau 2 is given at the inlet of the Cstr. The Cstr will produce an exponential decay, but it will be delayed by t equal to tau 2 because it has received the spike not at t equal to 0 but at t equal to tau 2. So, t equal to tau 2, this is C, and we will be getting this sort of curve, and this value is C naught, right, and the spike or this decay can be represented as 1 by tau 1 e to the power minus, C naught into e to the power minus t minus tau 2 by tau 1. So, these two, see, this and this are identical. So, obviously, E curve is going to be the same. E curve is going to be the same. So, what is our conclusion? Alternative to that, alternative to this RTD analysis, we have the inference. See, for reactions except fast order, I will discuss why it is not happening for fast order, except fast order, the outlet conversion in Cstr then PFR is totally different from that of PFR followed by Cstr. Therefore, we can conclude that RTD alone is not sufficient to predict the behavior of real reactors, because we have just seen the RTD of ideal reactor combination, if we change the combination, remains same in series, where RTD for these two reactors, two reactor configurations or two reactor combination remaining the same. But if I am conducting a reaction and for the configuration 1, this will be totally different than this one, except it is a first order reaction. Now, why it does not happen in case of first order reaction? For first order, dxa dt is equal to k into 1 minus xa. The rate equation is independent of concentration. So, concentration is a determining term, right? So, concentration, what is the local concentration is the determining term. If the rate equation itself is independent of the concentration, then no matter what is the residence time and what is the configuration, it will be actually immaterial, as in the rate equation we do not have any concentration term. But that will not be the case for anything which is having an order different from first order, right? They will be having, just like for example, if it is a second order reaction, we will have a Ca naught here. So, concentration as it is there, if it is present in the rate equation, then once we change the combination of even the ideal reactors, the outlet conversion will be changing. Whereas RTD is unable to differentiate between these two configurations. So, what does it mean? It means that we definitely need RTD, and RTD will give you what? The distribution of residence time. How long or what is the probability of a specific reactant packet to stay in a reactor for a specific interval of time, right? That is ETDT, we know what information RTD is providing. ETDT provides us the information about the probability, right, of a reactant packet to have a residence time between T to T plus dt. Okay? But how those packets having different residence time, they are interacting, that information is not included in RTD analysis. So, RTD provides the information about residence time of reactant packets. However, it does not elaborate, or it does not provide any information about how the different packets with different residence time interacts with each other. Which finally determines the concentration. So, that is why this is rather referred as mixing information, right. What will be the resulting concentration because of this interaction? That is basically mixing. Okay. So, if I have to model the real reactor, we need RTD, or primarily we need the kinetic data, that is the rate equation, plus RTD data or RTD information, that is basically the residence time, and we have to put a hypothesis about the mode of mixing or the degree of mixing, right, or both, and that is called the mixing models, right. So, mixing models means how these packets of different residence time, they are interacting with each other. What is our hypothesis? Whether there are definitely two extremes. One, there is interacting perfectly, right, perfectly mixed. Another, they are not interacting at all, that is complete segregation. However, there are intermediate. So, how to gauge those degree of mixing and how to determine the extent of mixing, that specific hallmark parameter of mixing from this RTD analysis, that we will discuss, and finally that will lead us to the modeling of real reactors, and that we will discuss in the next session.